chapter 10, and then we'll do our inverted lecture. So we've ended up with this slide where we were looking at stereochemical analysis of a free radical reaction for a molecule that already contains a chiral center. Now, when we're doing a free radical halogenation reaction on a molecule which does not contain a chiral center, and we generate a chiral center in that reaction, what must the products be? They must be racemic. However, when I already have a chiral center present, is it necessary that I generate the diastereomers in a 1-to-1 ratio? It is not. That is correct, right? And so, regardless of which hydrogen we remove, we're going to end up with that trigonoplanar carbon-centered radical, which is adjacent to a chiral center. So the top face of that radical and the bottom face of that radical are not identical. And so we can expect to see some selectivity in the reaction, okay? Y'all braved the weather together? There's an 80% chance that it's already raining? Okay. So we don't have to have equal amounts of the diastereomers. I am not going to expect you to do an in-depth analysis of that at this stage of your careers and determine which diastereomer you're going to get in excess and by about how much. That's stuff that you start learning about when you're in graduate school, okay? And so you can worry about it then. But what I really want you to take home is the fact that since these two things go through diastereomeric transition states, they do not have to be of identical energy. And so the one that has the lower energy transition state will be produced in the greatest amount or the least amount. Mm-hmm. Greatest amount, that's right. So if one of these, the transition states to one of these products had a lower energy of activation, we would expect it to be there in the greatest quantity, okay? So that's what I want you to take home from that. The other thing that we need to talk about is addition of HBr across a carbon-carbon double bond. And you're thinking, well, we've already talked about that, right? If I take propene and I take HBr, I'm going to get 2-bromopropane, right? And it's going to follow Markovnikov's rule. That's absolutely true. However, if I repeat that reaction, but instead of just using HBr, I add a free radical initiator, like peroxide, or I shine a really bright light on it, or I heat it up really, really high, I actually find out that I get the opposite material. I get the anti-Markovnikov addition of HBr across a carbon-carbon double bond. And the reason that this happens is because we're going through a free radical mechanism here, and what are we going through up here? Okay, and so what is that? What's the intermediate? Not a bromonium, because that would be Br2. What's the intermediate in the addition of HBr across an alkene in the absence of strong light? Follows Markovnikov's rule, so what's the intermediate? Yeah, I'd like the specific name for it, yeah. Carbocation, that's exactly right. Yeah, oh, you all knew this, right? Yeah, so here we're going through a carbocation intermediate, and that's why we get Markovnikov addition, right? Down here we're going through a free radical mechanism, and that's why we end up with the anti-Markovnikov. Now here in just a minute I'm going to have you help me figure out what the mechanism for that addition is, but we're going to do that at the end, okay? What I want you to take home from this is that if you want to add HBr across a double bond in an anti-Markovnikov fashion, you need to go through a free radical mechanism, okay? And this only works for HBr. HCl doesn't do this. Can anybody tell me why?
Because HCl would just get back into hydrogen?
Well, that can happen.
That's selective.
True. Why? What about the bromine radical versus the chlorine radical? More stable. That's exactly right. And so this reaction works much better for HBr than it does for HCl. And so if you want to make an anti-Markovnikov bromide, one way to do it, not the only way in the world to do it, but one way to do it is to do the free radical addition of HBr across a carbon-carbon double bond. We'll look at the mechanism of that here before we get started in our inverted lecture. Now, I want to take you back to a previous slide that we had at the very beginning of this chapter. Why is free radical chemistry important? Right? And for those of you who are going into medicine, it's very important because of things like this. Right? This is how arachidonic acid, which is a component of cell membranes, for example, right? It's a fatty acid that's very useful in biological systems, can undergo free radical oxidation using what's known as the COX-1 enzyme and ultimately give us prostaglandins. Why was that important?
Because that's what causes inflammation.
It causes inflammation, it causes pain, it causes fever, it seems to cause a lot of stuff, okay? And they're studying it a lot, right? Because we still don't completely understand everything that a prostaglandin does biologically. They are a very, very important class of molecules. But wouldn't it be nice if we could inhibit this process, right? We can, and we talked about ibuprofen being able to do this, right? But there's some other things that we can use that are in our diet that help prevent this process from occurring, okay? And one of them, if we call this an oxidation process, what things in our diet might we be consuming regularly that help prevent this process? Antioxidants, that's exactly right. And there is a whole group of people across the world that are studying new antioxidants for a variety of reasons, okay? The group that I was in at Vanderbilt had a subgroup that worked on the synthesis of better antioxidants that might have potential medical uses. I don't know if any medical uses have actually come from them. But one of the things that they were interested in at the time, I can tell you, was if you're in a car accident and you have a blunt force, blow to the head and your brain starts to inflame, one of the things that the doctors really want to do really, really quick is get that inflammation down, right? Because you're putting pressure on your brain, okay? What they wanted was a water-soluble super antioxidant that could travel through your system very, very quickly and help lower that. And that was one of the themes of that group. They were trying to find antioxidants that worked better and faster than the antioxidants that we normally consume in our diet. Can anybody think of the antioxidants that we typically consume in our diet? Okay, that's true. They're rich in antioxidants, but can you think of the specific antioxidants? Omega-3 is a fatty acid. It's like arachidonic acid. It's healthy for you, that's true. Anybody ever heard of vitamin E? Yeah, vitamin E. So if you put on those age-defying creams, I know none of you have to do that yet, but if you do that, what are they rich in? What do they say? Vitamin E. And it's because aging is caused by an oxidation process. That's why we wrinkle up and go rancid, okay, with age. I don't know anything about that, but that could be true. Okay. And so one of these, this is what vitamin E looks like. And it's a very good antioxidant. Does it have any chiral centers? Where? Any on the ring? No, on the main chain? Right, there's one. There's one. And there's one. It's got 3 chiral centers. And it turns out that the chirality is kind of important, okay? Natural vitamin E will be of 1 enantiomer. Synthetic vitamin E that you take is actually a mixture at each one of these stereocenters, because it turns out it is important, but it's not overly important that the chirality be correct for vitamin E to work, okay? You just need a fatty tail, because this is known as a lipid-soluble antioxidant. What does that mean, lipid-soluble?
It stays in your fat and doesn't go out.
That's right. It's a fat-soluble vitamin. That's exactly right. So it's not particularly soluble in water because it doesn't satisfy which rule that we've talked about? The 5-carbon rule. That's right. We have 1 hydrophilic group and a ton of carbon, right? So it's not going to be water soluble. And so this is actually transported in your body through little fatty globs, if you will, that are made water soluble by a protein wrapping around them, okay? This, however, is a synthetic variant of vitamin E. What's similar to this molecule and vitamin E?
It looks a lot like the
Okay, so this ring and this ring looks similar. What looks similar about them?
they've got an OH.
They've both got this OH. That's going to be an important part. What else do they have? Okay, so they've got some alkyl groups attached to the, so they're very similar, okay? BHT, butylated hydroxytoluene, is also a very powerful antioxidant. And this is something that they will add to canned and packaged meats, okay? Things that I like to eat probably too much, all right? So if you like those kinds of things, one of the things that they add to it is BHT. Can anybody tell me why? It's a preservative. That's exactly right, because sausages and things that taste good typically have a lot of fat in them, and fat likes to oxidize and go rancid, and I don't like to eat rancid sausage, okay? So they add BHT to it to stabilize it and to keep it. These are known as chain-breaking antioxidants. They break the oxidation propagation steps. They do not prohibit oxidation from occurring at all. They just break the chain so that it doesn't continue to propagate, okay? And they'll add some of this in there, okay? Now, the way that this works is that if you get a carbon radical, like let's say from arachidonic acid that gets formed in that first step from cyclooxygenase, okay? That free radical is an electron-deficient carbon, and it wants to have an octet. And so it goes after weak bonds, right? And one of those weak bonds is this OH bond in a phenol, which is kind of what we have here in vitamin E. That looks like a phenol, right? And so it will abstract the hydrogen, and you get what's known as an oxygen-centered radical, or phenolic radical, okay? And this radical is fairly stable and unreactive. Why? Bunch of resonance forms. That's exactly right. So you go from a highly reactive radical to a stable radical, and that's a much better thing, right? Now, it turns out that this radical can get recycled back into a phenol through another antioxidant that you all consume every morning in your glass of orange juice. What might that be? Vitamin C. And vitamin C is water soluble, right? So you have this cycle where the lipid-soluble antioxidant does the chemistry that it needs to do, and then at the surface of your cell membrane, vitamin C can recycle this back into vitamin E. At least that's believed how this occurs, okay? And so there's a lot of studies on how these things actually occur. What I want you to take home is that stable radicals, right, like phenoxyl radicals, make nice antioxidants, or come from nice antioxidants, I should say, okay? And so antioxidants, anti-aging formulations, things like that, sausages, you're going to want to put a lot of antioxidants into them, okay? Now, for those of you who are more interested in big molecules like polymers, free radical chemistry is going to be very, very important to you as you get into polymer organic chemistry. You're going to be talking about that to death, okay? And so free radical chemistry, you're going to be talking about the kinetics of free radical reactions, things that we really haven't been talking about in here. And I leave that to them to teach you, but I just want to introduce a little bit about free radical chemistry and polymerization. So, for example, we can make polyethylene by taking ethylene molecules and polymerizing them together. That can be done by a free radical mechanism. It's not the only mechanism you have to use, but it is a common mechanism for the formation of polyethylene. Can anybody think of anything that you use daily that has polyethylene in it? It's a very common plastic. Water bottles do. If you look on the bottom, it'll say HDPE. What does that stand for? High density polyethylene. That's right. Your gas tanks in your automobile are made out of high density polyethylene. Okay, they don't make them out of metal anymore because metal you can punch a hole in and gas goes everywhere during an accident. High density polyethylene holds up pretty good under car crashes, and so it works pretty well. Okay, and so you can see where the monomers actually end up in the polymer as shown here. So you just link all these things together through their double bonds, through a free radical mechanism, and you can make polyethylene. You can also make polystyrene. You can make polyvinyl chloride. A whole variety of things. So you take vinyl chloride, you polymerize it, you get water pipes or sewer pipes. You take propene and you polymerize it through a free radical mechanism and you get astroturf. You take styrene and you polymerize it and you get Starbucks coffee cups. Okay? You can get all of these products that we use through free radical chemistry by taking different monomers and polymerizing them. And the way that this works, how do we go from a monomer to a huge polymer? It's all about the propagation steps. Remember I told you how many propagation steps theoretically can we have? Millions, right? Many, 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 right? To use kind of a general, non-technical term, right? And so the way that the free radical polymerization step works is you typically have to start off with an initiator. Peroxides are a common way to do this. We know that the oxygen-oxygen single bond is pretty weak, and that breaks, and that gives me what's known as an alkoxy radical. That alkoxy radical will react with my carbon-carbon double bond, my monomer, okay? And what does that form? I go from an oxygen radical to a carbon radical. Pretty reactive, right? And so this is the initiation step. I go from no radicals to radicals. And now I've gone through this step where now I have a carbon radical. That carbon radical then reacts with more monomer and generates another carbon radical. And this continues and continues and continues. And I'll get a much larger molecular weight, right? And then at some point, after we start running out of materials, what happens? We start to terminate, right? And that's where the radicals start coming together, and we go from radicals to no radicals. And so we can get a wide variety of polymeric materials by free radical chemistry. And how you control the propagation steps and the terminations is what can determine the different properties of these polymers. And that's what they're studying across the street all the time. Okay? For example, Dr. McCormick studies a process called RAFT. Okay? And it's a way in which you can control the propagation and the termination steps, initiation steps, so that you can predict what the molecular weight of your product is. They like to target molecular weights because molecular weight is directly proportional to the properties that they're looking for, okay? So you don't want just a whole random distribution from very small polymers to very large polymers. You want a very narrow distribution of these things. And they'll teach you more about that as you get into classes over there. All right, so this really isn't a quiz. This is just a group exercise, all right? Walk me through what's going on in this mechanism. How can we take isobutylene, react it with HBr in the presence of peroxide, and get the anti-Markovnikov addition of HBr across the carbon-carbon double bond? Okay? What three steps do we have in free radical reactions? Initiation, propagation, and termination. So where are we going to start? Initiation. And what's going to be the initiator here? The peroxide, right? So in the initiation step, and I'm just going to call it IN, we're going to have ROOR, which is a peroxide, and it's going to go to what? RO what? RO dot. So I'm going to get two alkoxy radicals. We've just initiated the process. We now have free radicals to do the chemistry. Now what do we go into? We go into propagation steps, right? And so one of my alkoxy radicals is going to do what? What's it going to go after? Yeah, say it. That's right. And why that one? Because I know the bromine radical is stable. Okay, so this bond's fairly easy to break. So help me push the arrows. How am I going to push the arrows, Matthew?
Okay, so
which arrows am I going to use?
single bar, and you go from the
Okay.
oxygen, it's got bond over there between HBr, right?
Okay, and what else?
You gotta push it again off that bond. Close.
Right? And so what do we end up with? What do I end up with? What are the products? I get an alcohol plus Br dot. That's exactly right. That, by definition, is a propagation step because I start with a radical and I end with a radical, right? Now, the bromine radical now goes into another propagation step. What does it react with?
The carbon.
All right, so the carbon-carbon double bond. Now, this radical reacts at the terminal carbon, not the internal carbon. Can anybody explain why? There is. That's a true statement, but doesn't completely explain it. What do you think? What's stable? You're right. It's all about stability. What about it? I end up with a tertiary radical, don't I? If it were to attack here, what kind of radical would I end up with? Primary. And we know we're going to get the more stable radical, right? That's why it attacks this carbon and gives me this. And so now this radical reacts with what? To give me my product. What does it react with? What does it need? It needs a hydrogen. Where can it get it? Probably not the alcohol, but I can get it from the HBr, right? And so I end up with that plus the bromine radical, which does what? Comes back into this propagation step, and this occurs over and over again until what happens? Then we start to have termination steps. What are possible termination steps? There's many of them, but what possibly could happen in a termination step? I am running out of initial materials, that's right, but what things can come together to terminate? What two radicals? Two bromine radicals could come together, that's right, that could be a termination step. Two of these carbon radicals could come together and be a termination step. A bromine radical and a carbon radical could come together and be a termination step. You could give a whole series of termination steps. But the take-home message is that anything that removes radicals from the mixture, right, is going to be a termination step. Okay? And so that's why we can add HBr across a carbon-carbon double bond in an anti-Markovnikov fashion if we put a free radical initiator in there like a peroxide. Okay? Any questions about that? All right, go ahead and break up into your groups.